Okay, picture this. You take a glowing, red-hot steel ball and plunge it into a cool pan of water. Sizzle, steam, pure chaos. But what is mathematically happening inside that steel ball in those wild, chaotic seconds, right before the water and the ball reach the exact same temperature? You know, in engineering, we spend so much of our time focusing on the steady state, basically the calm after the storm. Well, today, we're going to totally shatter that illusion and look directly at the storm itself.
Welcome to our explainer on unsteady state conduction. Let's just dive right in. Because today, we are translating some seriously dense mathematical heat transfer equations into practical, actionable engineering confidence. By the end of this, we'll know exactly how to track heat as it actively moves through an object over time.
Here's a quick roadmap of where we're headed. We'll start with the unsteady state reality, then move to the lumped capacity method, tackle the semi-infinite solid, look at convection boundary conditions, and finally learn how to use Heisler charts.
All right, Section 1, the unsteady state reality, the chaos before equilibrium.
So the absolutely crucial point here is grasping the difference between steady and unsteady states. Think about it. In a steady state, the temperature profile is completely locked in. Heat transfer is constant, it's nice, it's predictable. But in the unsteady, or transient state, time is literally our biggest variable. The temperature of the body is actively, constantly changing. And that means our equations have to be modified to account for the change in the internal energy of the body over time. Almost every single industrial heating or cooling process out there has to account for this interim period.
Moving to Section 2, the lumped capacity method, where we assume uniform temperature.
Imagine an object just sitting there, cooling down in the ambient air. The lumped capacity method assumes that the internal resistance to heat conduction inside this object is tiny, basically negligible, compared to the external convection resistance at its surface. And because of this, we can assume the entire object is at a single, uniform temperature at any given exact millisecond in time. It behaves as one single lump of thermal capacity.
Actually, a thermal system perfectly mirrors an electrical RC circuit. It's so cool. The thermal capacity of our object acts exactly like a capacitor storing energy. When the object starts cooling, it's like a switch opening in a circuit, allowing all that stored thermal energy to dissipate right through the convection resistance at the surface, which acts just like an electrical resistor. Heat is the flow of energy, just as current is the flow of charge.
Let's ground this theory in reality for a second. When is that uniform temperature assumption actually valid? Well, take a small steel cube cooling in a normal room. Its internal conductivity is high, and the air's convection is relatively low, so it cools uniformly. Perfect. But now, think about a glass cylinder in a super fast airstream. Glass is a terrible conductor, meaning the outside cools way faster than the inside. The whole uniform assumption fails completely there. But swap that glass for highly conductive copper, boom, the assumption totally works again.
That relationship we were just talking about is actually something really special. It's called the Biot number. Honestly, I like to think of this as an engineering cheat code. It's a dimensionless group that compares surface convection resistance to internal conduction resistance. It instantly tells you if your internal resistance is negligible or not.
And right alongside the Biot number, we have a second cheat code, the Fourier number. Now, this one introduces time into the mix. It compares the characteristic dimension of the body with how deeply a temperature wave penetrates the material over a specific period. These two numbers, Biot and Fourier, are absolutely the keys to mastering unsteady state heat transfer.
So, what's the big takeaway here? It's this actionable rule of thumb. If you calculate your Biot number and it is less than 0.1, you can confidently use the simple lumped capacity equations. It'll give you a highly reasonable estimate, usually accurate to within about 5%. It's a fantastic shortcut. But what if your Biot number isn't less than 0.1? What if the object is just massive? Well, that brings us to our next section.
Section 3, the semi-infinite solid, when only the surface matters. Imagine a solid block of steel so unbelievably huge that for all practical purposes, it extends infinitely in one direction. We call this a semi-infinite solid. Now, if we suddenly drop the temperature at the surface, the whole block doesn't cool instantly. Obviously not, right? Instead, a temperature wave slowly, gradually propagates from the surface deep into the solid. To track this mathematically, we have to use something called a Laplace transform, which gives us an equation utilizing the Gauss error function. If we map this out, we can see exactly what that heavy math is doing physically. In those first few moments, the temperature drops incredibly rapidly right near the surface. It just plummets.
But as you move deeper into the solid, the temperature change slows to an absolute crawl. The surface feels the shock immediately, but the deep interior, it literally has no idea it's even cooling yet. Now, of course, true semi-infinite solids are pretty rare. In reality, we usually deal with finite objects.
Which brings us to Section 4, Convection Boundary Conditions, Navigating Real-World Geometries. We're going to look at 3 classic geometries, starting with a flat, infinite plate of a specific thickness, let's call it 2L. Because we're looking at convection happening on both sides of this plate, the characteristic dimension we actually care about is the half thickness, simply L. We take this L dimension and plug it straight into our dimensionless cheat codes, the Biot and Fourier numbers we talked about earlier.
And this brings us to the absolute climax of this whole explainer. Normally, to solve for the exact temperature of this plate over time, you'd need to calculate an intimidating, massive, infinite series. And let's be real, engineers hate doing infinite series by hand. Enter the Heisler chart. This chart brilliantly transforms that horrible math into a simple graphical lookup. You just find your Fourier number on the bottom axis, trace up to the curve representing your Biot number, and look to the left to find your exact midplane temperature. It is a thing of beauty.
And the coolest part is that this system applies to other shapes too. Next up, we have the infinite cylinder. Here, our characteristic dimension is no longer a half thickness, but the radius of the cylinder itself.
The exact same logic builds perfectly for the cylinder. Just like the plate, we have a specific Heisler chart designed solely for cylinders. You use the exact same analytical process. Calculate your Fourier and Biot numbers using the radius, trace your lines on the chart, and you effortlessly find the centerline axis temperature of the cylinder over time. No complex calculus required whatsoever.
And just to complete the set, yes, this absolutely applies to spherical geometries as well. A sphere uses its radius as the characteristic dimension, and it has its very own corresponding set of Heisler charts for calculating both the center temperature and the total heat loss over time.
Okay, so here is the crucial point to remember when using these magical Heisler charts. It's our final rule of thumb. Because these charts were generated by cutting off or truncating those massive infinite series solutions to save time, they are really only accurate if your Fourier number is greater than 0.2. As long as that's true, you calculate your inverse Biot number, check your chart, and you've got your temperatures. It is a massive, massive time saver for real-world engineering.
Wow. We've gone from the chaotic, unsteady reality of a sudden temperature shock through the elegant simplifications of lumped capacities and Biot numbers, all the way to visually mapping complex temperatures with Heisler charts. You now possess the tools to track the invisible flow of heat through time. So I leave you with this thought. If a mere fraction of a second changes everything in these transient states, how will you apply these principles to innovate and design the highly optimized thermal technologies of tomorrow? Keep questioning, keep calculating, and we'll see you in the next explainer.